Good afternoon to everyone. My name is Gabriele Guerrini, and I'm an assistant professor at the University of Pavia in Italy. For those of you who have not met me yet in the previous episodes of this webinar series, I work on the seismic analysis and assessment and retrofit of masonry structures. And today I will focus on what to do when we have to assess and possibly strengthen buildings that are found in the historical centers of cities. If you have followed the previous webinars of this series, probably you've already seen this slide. This is basically a summary of the framework that we find in the Eurocode 8 Part 3 for the assessment and retrofit of existing buildings. Now, today's talk will basically touch a little bit all of these points, starting from the knowledge of the building that we have to consider, going all the way through the local and global analysis, and finally to some hints about the design of retrofit interventions. So, when we talk about historical centers, we have to consider the fact that most likely, at least in European city centers, buildings will be clustered in what we call aggregates. This is very typical of our cities, of our historical cities in Italy as well as in other parts of Europe, but also in smaller towns, for example, on little villages on the hills and mountains. In all these cases, what we see is that our buildings are connected together. So they're not isolated from each other, but they share walls, or they're built against each other. And most likely, we may expect them to interact as they respond to seismic excitation. Now, the plan configuration of our historical centers and of our aggregates can be quite articulated, quite complex. So we go from line aggregates all the way to complex situations like these ones, where we have a number of internal courtyards between the buildings that form our aggregates. And of course, this complicates the entire process, starting from the knowledge of the building, its geometry and characteristics, all the way to the assessment and design of interventions. Things that complicate furthermore the situation are the different heights of adjacent buildings, different number of stories, the effect of the site morphology, especially on hills and mountains, where slopes, of course, force buildings to be built on different altitudes. And we have also to consider the fact that these building aggregates were not built all at once, but they are the result of a process that may have taken centuries to complete. So to simplify our considerations, we can think of some pre-existing cells, like the ones I'm showing here. And between these pre-existing cells, a second time, someone may have built some walls to also take advantage of that space, or an additional cell can be added against an existing one. So all this process, what happens is that most likely the connection between the walls, the pre-existing walls and the new walls at these locations here, here, and so on, may be not very good. We may have poor connections here that results in possible separation between these walls, even though it's not always the case, because sometimes we may have good connections, like in this case, with stones that are intersecting the interface. But you can see, like these examples, really poor connections. We can really understand where the pre-existing building or cell was finishing and where the new one is starting. You can definitely see the vertical joints here, also here, even though we have some plaster that has cracked afterwards. So in all these cases, we can definitely see that our joints are poorly connected. We may also instead have cases where this connection has been thought about. And so look at this building. You see this protruding stones. These are left there in case someone else or even the same owner had to add some additional room to its building, or an adjacent building had to be built. You see, these stones are ready to connect with a new wall built against the existing one. And here you can see the result. You see this stone here, this stone there, this other stone here. They're all crossing this vertical joint, providing connection between the two adjacent buildings. Furthermore, the situation can be complicated by the fact that the process is not that easy. So it may be quite spontaneous. Over the past centuries, there were no strict regulations in many cases. So there was no control on how, when, where these additional cells were built against the existing one. The process was quite really untidy. Moreover, over time, originally independent cells like these two may have been combined together, like in a new building with a fusion process over time. Or because of different reasons, some of the buildings might have been replaced with new construction. This is the case in historical centers, for example, that were bombed during World War II in Italy. We often find the situation of new modern buildings from the late 40s, 50s, and 60s built replacing older structures that were damaged or almost completely demolished. And finally, we may also see the situations where the owner of a specific building within the aggregate may have added floors to its structure. And this addition may be small, like in this case, where access to a roof terrace was created with these extensions. But we may have also other situations where almost the entire surface was added a floor, even though with misalignment between the walls here at the facade of the building. Or other situations can present a case where the extension, the additional floor, actually is aligned with the existing facade. So you see, we may have a bunch of different situations, and even within a single aggregate, depending on the building that we are considering, we may find different situations. So all this complicates quite significantly the entire process of knowledge and analysis of these buildings. So what do we have to do in case we are asked to proceed with the assessment and maybe the design of the retrofit for a building that is part of an aggregate? Well, first of all, we need to consider what the Eurocode asks us Annex C for masonry structures. And in particular, we can see that there are some aspects that are particularly relevant for aggregates. For example, how masonry elements are connected with each other, and if there is continuity or not in the load path through these connections, through these joints. This is a problem that we need to address. It's important to understand this when we analyze a building in an aggregate. Also, what are the different material properties that we may have within our building, also compared with the adjacent building, but also consider the fact that we have, remember, additional floors from different times in history. And so this may be associated to at least different workmanship or even different type of masonry. Now we need also to consider potential interaction with adjacent structures, and also how vertical loads are carried down to foundations, considering that there may be or no connection with adjacent structures. So all these aspects need to be considered in order to understand how different buildings, and in particular our building, is behaving within the context of the entire aggregate. Another aspect that may be of interest in this case is the connection between orthogonal walls, because due to the process of growth of the aggregate, we may see that at the intersection of orthogonal walls connection is not very good. For example, if a wall of a building was constructed against a pre-existing building without good connection. And also, and this is actually typical of almost all historical buildings, we need to assess the condition of the connections between walls and horizontal diaphragms, because due to the lack of seismic detailing in the past, these connections may be quite vulnerable. This is not only for buildings in aggregates, it's in generally valid for historical construction. Now, it is quite evident that if we are paid by our client to assess its own building, that we cannot have access to the entire aggregate, to other buildings that are owned by other people or by other businesses, and that it's also impractical to collect these informations required to model an entire aggregate. So of course, we need to limit our knowledge, we need to focus our knowledge to the building that we are analyzing. We don't find much guidance in Eurocode 8 about this issue. So I will refer to the Italian building code for this specific problem of how to focus, what to consider in this process. And what we find is that general methods that we use for isolated masonry buildings may not be so suitable for buildings in aggregates, and we need to follow specific rules, specific considerations. And in particular, an important aspect to take into consideration is the potential interaction due to structural contiguity with adjacent buildings. This is one of the main differences between buildings in aggregates and isolated buildings. So what we typically do is to identify a so-called structural unit, which is the one that we need to analyze and assess and probably strengthen. And once we identify our structural units, then we can also identify the adjacent ones. And so at this point, we can really try to understand, to establish the expected interactions between these structural units. So what defines the structural unit is, first of all, the vertical continuity of the load path for gravity loads. So understanding this may guide us into defining the structural unit, and also the fact that it might be identified by the presence of joints or open spaces or different construction technologies that really can tell us that that part of the aggregate is I'm not saying independent, but it's somehow autonomous compared to the adjacent parts. So we need to look into these aspects to understand again what can be considered our structural units, what can be considered adjacent units, and then to try to estimate the interactions between them. To do this, it's important to conduct a so-called critical survey for the aggregate, or at least for the portion of aggregate of interest. Meaning we should try to understand, first of all, how the aggregate has evolved during time. So to identify construction phases and to see, starting from this, if this can help us understanding where the boundaries between structural units are. For example, I'm showing here another example of an aggregate in a small town that has grown over time, And after conducting this critical survey, it was possible to understand that, starting from an original layout, floors were initially added to the original buildings in several phases, and finally the empty spaces between the different buildings were filled, and so a continuous facade was finally obtained, which is corresponding to the current state. This can be done by analyzing historical documents, records if are available, even though this is not usually going so far in history. But whatever information we can find from this kind of documentation, or also considering the materials that constitute our buildings. And so we can identify materials, structural details from different parts of the aggregates, and also for different parts of a structural unit in order to identify different type of masonry and floor diaphragms, which also can help us understanding what interactions we can expect among different units. And also within an individual structural unit, we may also be able to identify different materials that again are related to different phases of expansion of the building that we are considering. So you can see that this knowledge phase is quite delicate, can be quite difficult sometimes, but it is very important so to understand again what can be considered an independent, or if it's not independent because it interacts with other units, at least an autonomous structural unit. And starting from this can help us understanding also what interactions we can expect from the adjacent buildings. Now, how do these building aggregates perform in earthquakes? What information can we obtain from past events? Well, as we see from even recent or past earthquakes dating back even to the late 1800s, we can see that building aggregates in historical centers can be affected by significant damage. Damage that can be associated with the typical construction details of historical masonry buildings without good connections between floor, roofs, and walls. But also can be considered a result of interactions between adjacent buildings, like what we see, for example, in this case. This is from very recent earthquake in Italy in 2016 and 17 in central Italy. And again, we can see that our building aggregates can develop both out of plane overturning mechanisms, as the ones that you see here at the top of the slide, but also we can see that interaction between adjacent buildings can result in peculiar in-plane response due to, for example, pounding effects here at this location. So this is confirmed over time that we had interactions between adjacent buildings, and these interactions can be responsible of specific damage patterns. Statistical analysis from the 2009 L'Aquila earthquake in Italy has been performed with a quite comprehensive data set in terms of building typologies, looking at the construction age, number of stories, layout of the building, type of masonry material, the fact that buildings were isolated or part of aggregates. So a number of buildings has been considered in this study. We talk about thousands of buildings, like 26,000 and more buildings. So it's quite a comprehensive database. And we can analyze this data in terms of fragility curves. What is a fragility curve? Well, it's what we see here. It's a relationship between a probability of failure on the vertical axis and an intensity measure, in this case, the peak ground acceleration, for different limit states. The green curve here is for like operational limit state. The red curve is for collapse. Of course, the green curves are always above the other ones because it's easier to reach and to not meet this operational limit state at a given peak ground acceleration as opposed to the collapse limit state. And the same applies to the intermediate ones, like damage, life safety, near collapse, and so on. So a lower limit state is reached earlier, and so its curve lays above the ones for higher, more damaging limit states. Now, what we can see is that for any type of building in terms of regularity and quality of masonry, or low rise or mid to high rise, the fact that the building is part of an aggregate gives higher fragility, meaning that for any limit state that we consider, the curve is steeper. It approaches faster, a probability of 1 in terms of reaching a given limit state. So being in an aggregate makes our buildings more vulnerable as opposed to the case when buildings are isolated. So this means that the interaction between the adjacent buildings plays a significant role in making them more vulnerable to earthquakes. What has also been done in this study was to separate for the buildings that were part of an aggregate, separate them for the location, considering the location that they had within the aggregate. So considering corner buildings, end buildings, or intermediate buildings. And we can see that the situation is almost independent of the location within the aggregate. So we can see a difference between being in an aggregate and being isolated. Again, being in an aggregate gives steeper curves, meaning more vulnerable building, violating a certain limit state for a smaller PGA. But the location within the aggregate doesn't make a significant difference. Now, why we have these problems with buildings in aggregates? Well, we have seen that we have complex plan layouts, that we have irregularity in height, with adjacent buildings that are not of the same height, have not the same number of floors. Floors may not be at the same level in adjacent buildings. We see that we have an effect of the site morphology, especially if you are on hills or mountains. We have seen that these buildings have been transformed over time. Portions have been added, adjacent buildings have been built in different times, and also new floors have been added atop of original buildings. We have seen that this construction delayed over time result in poor connections. Well, all of this is cause of structural irregularity. And this structural irregularity plays a significant role on both global and local response of our buildings. If you look at the global response, for example, these irregularities may give rise to torsional and rotational modes of response if, which is often the condition, our diaphragms are flexible. This may result in distortion, in shear distortion of the diaphragms, especially at end or corner buildings or cells of the aggregate. We also see pounding and separation effects, depending on the direction of the earthquake excitation. You see, when we are accelerating toward the left, for example, these two buildings are pounding against each other, while if the acceleration is towards the right, they separate. But this pounding may concentrate damage at these locations, right above or below the vertical discontinuity. So this, of course, is making the situation worse than if the buildings were independent. Look at what happens when they separate. You see here we have a spandrel mechanism, which is not bad at all. But as they pound against each other, we develop a soft story mechanism here in this building, and also we damage the piers of the shorter building. So this interaction can be quite damaging, and this is why we expect to have, and we observe, more damage on buildings that are part of aggregates. These are some of the reasons. Other considerations involve the development of local out-of-plane overturning mechanisms. Now, typically in historical buildings, due to lack of detailing, we know that we need to check against these mechanisms that may vary from simple overturning of individual facades or portion of facades to combined overturning of walls and portion of intersecting walls. We may develop mechanisms of arching and bending, both with respect to vertical and horizontal axis. But in the case of aggregates, we have specific mechanisms that again develop because of the interaction between the buildings. For example, pounding between a taller and a shorter building may give rise, we will see this, to particular overturning effects on the upper portion of the taller building, for example. So again, the fact that we have interaction, that we have different heights for adjacent buildings, that we may have poor connections between walls due to delayed construction over time, all this may make the development of this local mechanism even more worrying than for isolated buildings. And this is what we have seen again in recent earthquakes. This is from L'Aquila in 2009. We can see that we have separation along these joints here and there. Here we have damage due to pounding between these two different height buildings. Look at this facade. Here it's separated, and you see this portion of the wall is trying to overturn out of plane. Probably the intersecting wall here was well connected to this part of the facade, the original building. Maybe this one was added afterwards and not well connected at all, so it overturned. Look here again, another effect of pounding. So this is for like longitudinal motion along the aggregate dimension. You see this effect here on the upper part of this building. And again, in 2016, similar observations, pounding effect here, separation along these vertical joints, overturning mechanisms due to poor detailing, and again, separation and pounding at this location. So we really need to be careful, and we need to consider with attention these interactions between adjacent units, adjacent buildings, even though our attention will be focused on the units that our client owns. Now, this is a particular consideration, a particular example from the 2012 Emilia earthquake. That earthquake sequence was characterized by two main shocks at about 1 week of distance from each other. In the first shock, look at this end unit started separating from this one. You can definitely see how the connection was realized here with very few locations and very poor in terms of ability of keeping the two units connected with each other. After the second shock, this portion of this unit completely collapsed. It separated from this one. Probably the floors lost support, and you can see the collapse of this unit. So, given this, how do we proceed in the analysis? So we have seen that we need to be careful in gathering information about our structural unit and about the adjacent ones in the aggregate. Now, how do we proceed with modeling and analyzing for a global response our building? Well, once we identify our structural unit, we need to see what are the effects coming from the adjacent ones. This is the main difference, because one may be tempted to analyze the structural unit independently from any interaction with the adjacent ones. But this may not be conservative in some cases, and we will see examples on when this is conservative and when this is not. What are the interactions that we need to take into account? Well, first of all, we have thrusts that come from the adjacent units. They might be due to arches, walls, roofing systems, and they may not be balanced by equal and opposite thrust coming from our unit. So these unbalanced thrusts must be taken into account. Then we may have to consider local mechanisms due to facade misalignments and effects of different heights and different stiffnesses among units. For example, again, specific overturning mechanisms, like the one that might develop here, but also pounding effects, separation and pounding effects. So all these interactions should be at least considered and somehow modeled the analysis of our building coming from an aggregate. Now, if floor diaphragms are very flexible, ideally infinitely flexible, we can analyze individual walls separately. Basically, we can neglect the coupling provided by the floors. If we do this, then each wall must be analyzed considering the tributary gravity loads and also the tributary masses that will give rise to the seismic actions. But we can do this. And actually, in some cases, we should do this. So let's start considering a very simple example. This is an analytical study for a building aggregate with well-connected adjacent buildings. And first of all, we can consider the analysis of individual cells. In this study, there were two cases. One where the cell was very simple, like this one. The second case, the cell, the elementary cell, actually consisted of two rooms. You see, it's a three-story building with these two openings that on one side it's a door, on the other side is a window. And this causes some asymmetry between these two walls. Same thing for this other case here. Doors on one facade, actually on the interior wall, then windows on one facade and windows and door on the other one. This elementary cells, let's take the simpler one, can be analyzed in the longitudinal direction, which is this one here. The aggregate will be formed by adjacent cells in this direction. This is our longitudinal direction. This is our transverse direction. Analysis can be carried out in both directions. Of course, the transverse one is quite stiffer than the longitudinal one in this case. You see a different order of magnitude of displacement in those directions. One may be tempted, in a real case, to just analyze the individual cell corresponding to the property that is contacting the engineer. However, let's look at what happens if we consider this unit as part of aggregate. Now, three situations were considered: a 3-cell aggregate, a 5-cell and 9-cell aggregate, with both single room and double room elementary cells. But again, let's consider one of them for simplicity. And let's focus on the 9-cell case. Now, for each cell, the in-plane distortion, shear distortion of the floor diaphragm can be found. We can see that it is maximum for the end units, and it's almost zero from the central one. So this is telling us that end units and intermediate units are behaving differently. And if we compare the shear distortion of the floor diaphragm coming from the individual cell analysis and from the aggregate analysis in the two directions, we can see that in the longitudinal one, it's actually conservative, considering the individual cell, but it's not in the transverse direction. Here what we see is the association of the distortion with the PGA. So you can see that if we consider the individual cell here, the same PGA causes a smaller displacement than on the aggregate, the same smaller shear deformation. But that's not the case for this other situation. So you see here for the single room, this is for the double room. Okay, single room, individual cell, single room aggregate, double room individual cell, double room aggregate. Again, distortion from the individual cell greater than in the aggregate. Distortion from the individual cell greater than in the aggregate. This is for the longitudinal direction. But we have the opposite when we consider a transverse direction. You see, single and double room individual cells here. But now, if we put them in an aggregate, the distortion of the diaphragm will be larger. So we have a larger demand. And for the same PGA. And that's a problem, because if we analyze an individual unit without any interaction, well, in this case, we are missing the point. We are unconservative. Now, in this case of a well-connected aggregate, there is an easy fix for this problem, because it comes from the fact that interior walls have larger tributary masses than end walls. So what we can do is just analyzing individually the interior and the exterior wall, as the floor diaphragms are very flexible, so we can do this independent analysis of the two walls, and then we will find the responses for the two of them, and then since we have differential displacement, we can find the distortion of the diaphragms, just putting together the results. And if we do this in the transverse direction, we obtain, these results here from this so-called effective cell. And they compare very well with the results that we obtain on the 9-cell aggregate. The maximum distortion, of course, is for the end unit, where we have an exterior wall and an interior wall. You see very, very similar results. So actually, by doing this, we can solve this problem. Again, in this case, the interaction is in terms of tributary mass and tributary loads on the interior walls, because they're resisting also the inertia and the weight of the adjacent unit. And if we don't think about this, we just extract our unit without considering what comes from the adjacent one, we make a mistake. But we can solve it this way. Now, in this specific case, there were no problems in the longitudinal direction, because let's go back, you see, we have good connections. So when we put together two adjacent units, we end up with a very large pier here, here, and there. So all this location, compared to the individual cell, where the piers were narrower, we have longer piers, which make them stiffer and stronger. So in this case, in the longitudinal direction, it's actually conservative, analyzing an individual unit. But again, it's not in the transverse direction, unless we consider the different tributary masses and loads acting on the interior and exterior walls. So be careful to this. Now, what happens if we stiffen the diaphragm in our aggregate? So let's consider another example to understand this. Again, we have an individual structural unit, which is comprising basically 3 rooms, 2 rooms and a stairwell, and a 5-unit linear aggregate, just obtained again replicating the individual unit 5 times. We shared party walls, similar to the previous case. Let's start considering the case of very flexible diaphragms, for example, timber diaphragms or vaulted ceilings. Now, if we do this with flexible diaphragms in the original configuration, the individual unit will deform like this. We have differential deformations between the end walls and the interior walls of the unit, of course, because of the presence of openings here, and also different tributary loads. If we stiffen the diaphragm, for example, by adding a concrete overlay, then all walls will be forced to move almost by the same amount. And so the deflected shape of the diaphragm will be this one. It will not deform, it will just move as a rigid body in its plane. This is for the individual cells. Let's look now at the entire aggregate. So what we see is that the end walls remain nearly undeformed. This is the result, for example, of a pushover analysis. See, end walls, green, almost undeformed. You can see it also here in the diaphragm deflected shape. While all interior walls are basically displacing, you see, like similar amounts, meaning that the interior diaphragm, the interior cell diaphragms will almost remain undeflected, like this one. Most of the distortion will concentrate at this location. This is the same as we saw before. So this is where we have problem, for the same reason that we already discussed. This wall has a smaller tributary mass than the interior ones, so it will deform less. And all the difference, or most of the difference, will be accommodated by distortion of these two diaphragm panels. Well, one may be tempted then to strengthen only the end diaphragms. And this may be a problem, we will see it, because if we stiffen the entire aggregate, you see, we move from a flexible situation like this one to a completely rigid situation like this one. The whole building, the whole aggregate is moving together. We may have also intermediate situations, but the effect is basically to mitigate the distortion here and there, just reducing the overall differential displacements. But if we strengthen only the units where we were having problems, this is what happens. We are just shifting that deformation from the end unit to the adjacent one. Now this one is stiff. You see the diaphragm is almost not deforming. Now we are just moving the problem. We are not solving it. So we need to be very careful when we design our strengthening interventions, because we may solve the problem for our client if he or she is the owner of this unit, but we may worsen the situation for our neighbor, or the other way around. Our neighbor may have strengthened and stiffened the diaphragms of its building. This may cause problems, additional problems for our building. So be careful to that. These are things that should be considered. Of course, it's not always possible to know if someone in the past has done any intervention on the floors of an adjacent building. But unfortunately, this information could be quite important if we are the owner of the second one. It would be quite important to understand if our neighbor has changed the stiffness of its diaphragms. Now, finally, how to model the interaction between adjacent units, not only in terms of tributary masses. Say, if we can expect separation between the units. Well, we know that it's impractical to model the entire aggregate, and so we need to resort to modeling only our structural units. And we need to somehow take into account these interactions that we have been talking about. So how can we do this? Because we will have information about, say, this portion of the aggregate, the one that we are going to assess and probably strengthen, this one here in plan view. We may not know much about the rest of the building, and there might be interaction over here. So how can we address this problem? Well, again, two roads. One, just ignore an interaction. But we said this might not be safe. Interactions can play a significant role. We saw this already in the previous examples. So if we don't have enough information about the adjacent unit, we can try to apply some simplifications. For example, we can introduce some equivalent restraint to our unit, like modeling, for example, with truss elements, the stiffness and the strength of the adjacent unit that is interacting with ours. And this can be done again with truss elements, with stiffness and strength representative of what we expect just from observation, sometimes geometrical observation from outside of the adjacent portion. Now, if we expect separation because of poor connections, these elements can be no tension elements, so reacting only in compression when the two units are pushing against each other, or if by inspecting the connection we see that there is good interlock, we may also model some tensile strength based on what we expect for our masonry. So this is a possible, say, compromise between just going from the maybe a conservative solution of ignoring the interaction and modeling the entire aggregate for which we don't have information and access. And it's important to do so because look at what happened if we model the interaction like that, with no tension trusses in this case, so reacting only in compression. When we consider the direction perpendicular to the joint, this is the joint. So we are moving perpendicularly to the joint. Away from the joint, there is basically no difference. There is no influence by this model. But when we push against each other, you see here we have a restraint, but the restraint is not affecting the entire facade, only this portion. And this will result in torsional effects on this unit that we would not capture with this amount if we ignore the interference, the interaction. We would obtain something similar to this also in the opposite verse. While in the direction parallel or nearly parallel to the joint, again, we have no influence by this model as expected. So it's important to consider this, even with a simplified model. But at least this gives us information about what we may expect. In this case, torsional effects, for example. It's really important to do this. And finally, a few considerations about local mechanisms in our buildings, especially within the context of building aggregates. Again, we may have like conventional mechanisms developing, for example, the overturning of this facade, as you would probably find also in an isolated building, but also mechanisms that are typical of interacting buildings. For example, say overturning of portions like these ones that are above the adjacent unit, or these ones here that we see we have partial restraint from adjacent units, and this may cause overturning of portions only of facades, or even pounding effect may exaggerate this type of response. Also, we may develop mechanisms due to subsequent vertical growth of the buildings, like in these cases, or misalignments of facades. Again, several situations, or poor connection, like in this case, maybe the intersecting wall was part of this building and this part of the facade was added afterwards. So all these considerations, again, can help us understanding if one mechanism will develop or not, and to which extent we need to consider it. So again, knowing details about the connections and about the interactions is really important also to understand which mechanisms, local mechanisms, will develop and which portions of our walls will be interested by these mechanisms. And again, typically we start from loss of cohesion and material disaggregation, which is typical of old, poorly constructed buildings. and then we have total or partial overturning of facades, or if we have somehow decent restraint from floors, we may develop arching and bending mechanisms. We need to take into account the adverse effects of thrust from walls, arches, inclined roof elements, and so on. And also, I will repeat it, adverse effects due to interaction between adjacent units, for example, pounding. All of this is important to understand what to analyze. It's really, really difficult sometimes to identify possible mechanisms, but we need to do that. So a few examples, it is like loss of cohesion and material disaggregation, is typically observed in stone masonry buildings, but also in large thickness brick walls if we have loose filling materials. And we have overturning, again, you see, with detachment of a facade from the transverse walls, entire facade or a portion of facade. Look at this case. For example, this transverse wall is part of this adjacent cell. This transverse wall is part of this adjacent cell. Our building, this one, might be built just with a wall poorly connected to the pre-existing ones, and it will overturn like this, for example. But these mechanisms can also be triggered by opening that are weakening the facade. So all these considerations, as usual, as I already said, need to be made by the engineer. Combined overturning mechanisms, which involve not only the overturning facade, but also portions of the intersecting walls, which may have different shapes and different configurations depending on the level of connection between intersecting walls, between walls and roof, walls and floor diaphragms, and so on and so forth. Again, in this case, look, what may happen if the connection fails at this location. We may lose all this portion of the facade. It's a complex geometry, but it may be worth it to analyze, even though it's not that immediate. Effect of misalignments on overturning mechanisms. Look at this case. If our facades are all aligned, you see, we excite the building, the aggregates in the longitudinal direction. Well, the inertias in this facade will somehow be resisted by the adjacent ones, and the load path will be something like this. And there will be no overturning in this direction. But if we have a misalignment, this portion may just move away and fall down. We may have overturning limited to this corner portion. This is just because of a misalignment. And this is especially true when we have set against portions in our aggregates that may separate from the main structure and may again overturn and collapse. Horizontal and vertical arching mechanisms also need to be taken into account. And again, considerations should be given to connections with floors, roof systems, with adjacent buildings, with transverse walls, as said before. Now, effects due to pounding. So buildings hitting each other in the longitudinal direction of the aggregates. You see these effects here, cracking in this direction, in this wall, due to the interaction here, but we may also develop, you see, for this portion, an overturning mechanism just in the upper portion. And this might be made more vulnerable by the fact that pounding introduces higher accelerations at this location because of the impact. So we should be at least careful into analyzing this possible mechanism here. Then we have pounding mechanisms involving floor members, which may punch through supporting walls. We may have pounding from roof structures on longitudinal walls of the aggregate, on gables, on corners, and this may be made worse if there are unbalanced thrusts from just the static behavior of our roof systems, like with these inclined purlins that are missing a tie and so are pushing our walls outwards or our corners outwards. This may cause a higher vulnerability. It adds to the dynamic effect of the seismic excitation. Finally, a few images from interventions that may be not so effective, or they may even make things worse. And this involves especially the replacement of roof and floor structures that were originally light, for example, timber systems, with concrete structures and concrete ring beams. They are characterized by high stiffness and high mass. This may result in large forces transferred to the masonry, and these forces may exceed either the frictional capacity at the interface, like in these cases, but we may see even worse situation. Look at this, collapses caused by the interaction between this stiff concrete ring beam and the supporting masonry, which was not strong enough to resist those forces and then collapsed under those excessive lateral forces. Look at this case. Now, the roof is still standing because of the stiffness and strength of the ring beams, but otherwise this would have collapsed. The masonry has totally collapsed here. Here, the same thing. So we need to be very, very careful. We should avoid, actually, adding mass and excessive stiffness in this way, because this has proved to be worsening situation. If we need to increase the stiffness of a timber floor, for example, we may add timber overlays, or even a lightweight concrete topping, but not replacing the entire timber floor with a heavy concrete or concrete and hollow clay block structure. And we should avoid these stiff ring beams that are, again, destroying the masonry below. And another thing that we should avoid are this ring beam built like within the masonry thickness, especially if they are supported only on the interior leaf of the masonry. Because what happens when we build these members here, we need to remove part of the masonry. We are altering the flow of forces, of gravity forces. We are overstressing the outer leaf, and also we are making it prone to buckling. When we build the new concrete floor with the ring beam, we are now loading with the new floor only the interior leaf, but whatever was deviated towards the outer leaf is not going back to the interior one, even if we close the gap here. So if we do this, we risk that once our floor moves because of the lateral forces, it's hitting, it's pounding against the outer leaf, which was already overloaded, and it will buckle outwards and it will collapse, like in this case. So we really, really need to avoid this kind of intervention. If we need to provide a ring beam at intermediate floors, we can do it within the floor, the diaphragm panel, not inside the masonry. We can add L-shape steel angles, for example. We can add reinforcement within concrete overlay along the perimeter of the floor diaphragm, but not removing the masonry, not adding this ring beams, concrete beams within the thickness of the masonry, because this is causing problems like we see here. So we should be very, very careful when we do this. And this is not only valid for buildings in aggregate, but in general for historical buildings, when we need to stiffen and strengthen our diaphragms, but we need to do it with care. So both choosing the type of intervention and also choosing the location. Remember what I showed you before. If we stiffen a unit, we may cause problems to the adjacent one, or the other way around. If someone has stiffened an adjacent unit, it may cause increased vulnerability to the unit that we are assessing. So be careful. And with this, I have concluded